the slides are, the first slide is shown. So I go over to the second one, which is the content of the slide. This is the way that the presentation is structured. So some definitions, of course, objectives, properties, etc. It's a usual way of doing a presentation, I would say. And you know that I like this picture very well, very much.
Yeah.
Then, and it comes from in this case from Wikipedia. But I have the book of Brian Castellani, so it comes out of his book. And what is fascinating is that this is about 50 years, yeah, something half a century. What has evolved since, let's say, the 1960s up to 2012 or 10. And I positioned top left, the first report of the Club of Rome, so the limits to growth, with the purple dynamic systems theory. And it was, at that time in 1972, absolutely innovating by J. Forrester at MIT. And so a lot of things are on there. Then I brought the yellow part in the middle, located in the complexity science, and then jumped over to what we are now considering to new science of networks. That was the previous one. And the one before, complexity theory, epistemology. But let's say, leave the word epistemology, but so we are more talking about the science. And then the global network society, with a colleague, I absolutely, is excellent, is Immanuel Wallerstein, but he's getting it by the 85 or so, and he's located in New York. So, other names there, Manuel Castells, for those in information technology, is there very well known, is located in, I think, in Barcelona. And then others, names, Strogatz, I see there, Barabasi underneath. These are well-known authors now, Barabasi in particular, on network science. And so we come later to that name. Duncan Watts as well. Duncan Watts was in the beginning, and still is in part, at the Santa Fe Institute in New Mexico, which is a leading institution, research institution, since the very beginning, with the Murray Gell-Mann as Nobel Prize Physics and co-founder, or let's say co-founder. Other names which will come up with the autopoiesis and self-organization, a little bit more to the left, but still in the yellow part, is Stuart Kaufman. Stuart Kaufman is superb, is excellent. And so in biology, microbiology, and innovated there the concept of complexity and autopoiesis or self-organization. With other names below, also the yellow, Francisco Varela and Humberto Maturana, both from Chile, is written in parentheses, cognitive science. Both are neurophysiologists. One of the two died. I think it's Maturana, but I'm not sure. So this is, that we are in the 70s, 75, something like that. This is absolutely, what we see there is, let's say for my age, is completely new. What has been discovered in knowledge, but what has also been discovered in methodology, in research methodology. This is up to me, even when I'm exaggerating, is fabulous to see that what has happened in 50 years. Now, the lower part, I'm reading a book on that, agent-based modeling. And so the research project I try to launch will have to do with that. And is very mathematical, so I'm a chemist, so I'm somewhat an outsider. But there is a lot going on in a nonlinear correlation description in sophisticated situations. So I give an example, and the weather description. So the weather descriptions is a very good example in nonlinear behavior and interactions among many parameters. Another one is that in social sciences, also what we have said in QST, social sciences in that part is going a metamorphosis, that it is going away from description, verbal descriptions, but with quantitative mathematical input, and to discover in the system what correlations and interactions mean and how they are, etc. So this picture, I do find it absolutely fabulous to see what has happened in half a century for those who were active at early times. Another here is also from Wiki, so the reference is in blue-below, and gives a number of elements or domains, I would say, of complex systems. And so where I feel at a little bit at home is in networking, yeah, but there is systems theory, where another element of entropy, it's left to the left down, systems theory, where things, from my background, entropy, autopoiesis, computation theory, complex measurement. So this is also something where, let's say that I feel at home. Yeah? Nonlinear dynamics is for real mathematicians, mathematics-liking people, where something as a bifurcation, where at the time, not so long ago, Ilya Prigogine, Nobel Prize of Chemistry for theoretical chemistry, came up with that and brought in very new insights in what is happening, really. And then others, I leave that for those who are interested. I have no knowledge about game theory, but anyway, these two pictures are, let's say, from the spirit, somewhat theoretical. However, especially in social science, but also in exact sciences, and in political and, let's say, domain, new applications, new methods arise to investigate what's going on in society. This is then very, very practical, and although sophisticated, but very, very practical. So I come there too, or we come there, you and myself, at the end of our presentation. But imagine that these tools would have been applied to the banking system 5 years ago, with seriousness that people from the banking would listen to scientists, which is not sure, or politicians would lead. But nevertheless, we probably would have better understanding of what was going on. Good. Yeah, well, these are some thoughts brought together. Yeah, they're nice to read, I would say. Not too long to remain to that. So Stephen Hawking, you know that, and so he was asked a question about the future, the 21st century, but the question was asked before. So will be the century of complexity. So this is a stimulating description from his part. Then the social science, I've mentioned that. the statistical methodologies of natural sciences assimilated, while it has enhanced the social science, it has fallen short of capturing complexity. So we are beyond statistics. We are beyond what the statistics as, I would say, classical statistics, which did their entrance in psychology, strongly, at least in the faculty at my university. So they have a very strong education in statistical methodologies and statistical mechanics for statistics, but fallen short as a statement of capturing complexity. So there is more than that, than the statistics event, that hopefully becomes clear. And then another thing is integrate individual behavior in social interactions. Is also an element to be discovered. I read a paper where an analysis after an election was done about the election, that some knowledge can be deducted of election or of democratic processes. So then the agent-based modeling raises serious questions concerning the application of rational choice models to human economic actors. So we all are interested in new economic systems, and many people talk about it. And so I just wonder, I don't have the answer, but if that doesn't apply or have an open window to complexity approaches, I fear that we are turning around. This is a feeling for my part and a comment for my part, so nobody is responsible for that except me. So these examples here, or statements, most have to do with social sciences. The others, as I said, about weather and other things, they're still there. Now, when I prepared that, it is not so easy to find understandable definitions. It is not easy yet at this stage. And here which comes from Wikipedia, by the way, but at the end there is a small table of references of excellent papers, large papers from the OECD, for example, and others. And so there, complex systems is a new approach to science that studies how relationships between parts give rise to collective behaviors of a system, and how the system interacts from relationship with its environment. That environment should be more clear. Now, one thing should be clear, that is that complex systems, these analyses, do not interfere, do not change the data. The data remain what they are at the start of the method or the analysis or a modeling. So it is looking after interrelations, correlations between these data. So some physicists say, well, you know, when we have a model in physics, what can happen more? So what do we need more? That was with a colleague at the university involved in climate change. And so his classical, I would say, attitude is that when the physics can describe satisfactorily or exactly, but such phenomena, then we have the reality, and this is not true. So the complex systems analysis, the networks, give other insights how a system is behaving, is constituted actually. So it are interactions, it are relationships without intervening with the data as they are presented. And then the second part, the equations from which complex system models are developed generally derive from statistical physics, information theory, and nonlinear dynamics, and represent organized but unpredictable behavior of systems, that should be in blue as well, I see here, represent organized but unpredictable behavior of systems of nature that are considered fundamentally complex. So it has to do with new insights. Yeah. The shadow is that one has to be familiar with mathematics. And this is a problem which I experience as a chemist. I have not been trained enough in mathematics, but still much more than sociologists. So, but to be clear that there are no, let's say, wrong expectations of applying and getting into that field. This is from a publication here. It's Weisbuch and Salomon, 2007, where a number of names are there. And so the early names, we know von Neumann, for in the computer sciences, the Turing machines and Turing conditions are known. The perceptrons, I don't know, I passed that, but Kaufmann is there. Co-founder of the Santa Fe Institute, is superb in approaching the nonlinear systems. And then the others, I don't know, Parisi, Replica, and other, these are names. It just to, I brought this here, so the beacons, I don't know them all, far from. But so there's a manifold of scientists underway and still now growing quite a lot. So this is, with a reference, an excellent publication. Objectives, this is point 3. Some caution should be used in keeping in mind the difference between the real world and complex systems and their models. So this is what scientists say, which is, I do find an expression of modesty. Even at the end, from a quotation, which I bring in here, but in the end, stated in some way with humor, is that all models are wrong, but some are useful. Well, you know, you have to take that with some humor, but okay, so we are understanding, or the cognitive part of it, we cannot escape from models. This is my personal meaning. So if someone else can comment on that, it would be fine. But so this here makes this in Weisbuch and Salomon. They are both in Paris, I think. Weisbuch certainly, Salomon also. But anyway, so to caution that we do not draw conclusions, hazardous conclusions. Models. Okay, complex systems are composed of a very large number of different elements with nonlinear interactions. So nonlinear, so to give an example of nonlinear, we know all, is population evolution. So we know that. Now the world population is growing extremely fast. So we know that some say it is exponential, but this is not correct. It is an hyperbolic correlation. So this is an example we're living all the day. So the nonlinear, although in other applications is quite sophisticated and mathematics, but still actually we can see it, but we don't see it. Well, we can see it. So good. Furthermore, interaction structure, a network comprises many entangled loops. Maybe I bring in here the first report to the Club of Rome, The Limits to Growth, which was done at MIT with Jay Forrester, and then the young postdocs, actually, Meadows and others, brought in the notion of loops. So what is the dynamic system? The dynamic system evolving in time, of course, but in this case, and that was new at that time, that with loops are working back and bringing in new perspectives, projections, and not indefinitely so, but at least the effects are clear. So in the case of limits to growth for the population has an effect on the 200-year scale that was used at the time with loops. How the population is evolving and what their numbers at a given period of time have an effect. So just a comment to nonlinear, that to clarify that if necessary. The purpose of complex system research is to propose and to solve models such that we can deduce functional organizations from the interaction of the components. Purpose is to propose and solve models that can deduce functional organization from interactions. Again, complex system theory often addresses the issue of restricting predictions to generic properties. Important. So, in the case, I refer to the first report of Raoul. There are no predictions. There are scenarios, and a scenario is more modest. And when you have a model, you can make many scenarios. One so far, it is easy to make scenarios, but these are painting an evolution and trends, which are very useful, but they are not predictions. It's not going to happen in 2050, etc. So restricting predictions, very important. And then a jump to thermodynamics. Thermodynamics is not only a theory about work and heat, but it applies to all physical systems: gases, liquids, solids, electric, magnetic, and elastic properties. So I leave that for what it is, but in fact, statistical mechanics, the microscopic theory behind thermodynamics, the microscopic theory behind thermodynamics is probably the closest theoretical analog to complex system theory. So there is a jump to real physical reality, the thermodynamic reality, and what the objectives are of a complex theory. And so a double dot. Its purpose is to reduce microscopic properties of matter, the thermodynamics, from those of its individual components, as atoms, molecules, and polymers. So this is quite analogous to social sciences. And Ilya Prigogine, at the end of his life, he was very committed and interested in social sciences. And he tried to have cross-fertilization between his thermodynamics approach of physics for physical realities to social environments. So the social is also individuals, and there, instead of atoms or molecules, these are the individuals consisting of a group or a society. That comes from Weis' book as well. So next, this is a picture from the same publication. It's somewhat a metaphor. The different fields of research, say biology, sociology, physical chemistry, optimization, share many traits when checked from a complex system perspective. This is illustrated by the large overlap of two-dimensional projections on the XY plane of the four spaces in a 3D. So this is a projection down that is shown there. So it is not a revolution what we see there. However, up to now, and so I refer that to the Club of Rome, so the inspiration, where I said we should approach reality in an holistic, so as from science and knowledge, from an holistic way of thinking, holistic, having an open eye for totalities, for globalities, and and even the research up to now has been structured along specific topics. What is called the reductionist to reduce it, reductionist approaches, which is here presented in the 4 circles and projected down. And there we see, in this image, where they overlap. And complex system analysis has the objective, idealistically, that's to handle that, to address the let's say the correlations between the interactions, which is not visible, which are not made visible by the separate approaches here mentioned in the four circles. So this is simple, is somewhat simplistic but it illustrates. And so why we bring that here is that just to have a correct understanding as possible, so much as possible, that the complex systems is bringing something more than the usual classical sciences do. And this is the novelty, and if I feel right, this is opening a lot of future analysis of our societies. Okay, here, so in total there are 26 presentations, which is quite too much. So let me try to find out from different publications. One is from the OECD, which is absolutely very, very excellent. It's available on the internet. So the summing up of what complex systems, their properties are, or their structure. And so I will sum them up without too much comment, and otherwise I'm taking the format too long. But social, political, ecological, economic systems involve much mutual adaptive interaction. Adaptive, the word is important. Interactions. And produce characteristic pattern. The promise of complexity science for policy applications is the perspective that science can help anticipate and understand key patterns. Here is even the word anticipate used, so which is strong, but okay. And understand key pattern in complex system, and thus enabling wiser decisions about policy intervention. It is a fantastic statement, a far-reaching statement. Then we don't have it. And so, my opinion is our politicians are in many countries, but I still take Belgium, are underdeveloped people. They are not have not the maturity, intellectual, cognitive maturity to deal with the complexity of the problems the society is bringing them. These are strong statements, but it's other words as what is standing there. Okay, good. Then I just go through, then there are 3 or 4. So adaptability are formed in independent constituents, I have said, that interact. Adaptability, very important. It changes over time. Yeah. Emergence, novel pattern, not predicted by fundamental properties. Yes. Self-organization, that will be another workshop. So sometime at the end of the year. Mutually adapting constituents is called self-organization because no entity designs it. Self-organization because no entity designs it. Fantastic, yeah. Very strong, by the way. Yeah. Okay, so they will adapt autonomously to changing conditions. These are concepts which are used in the evolution of the living world. Yeah. So okay, but that's for later on. This is also very fascinating. It's attractors. There are some interactive relations that attract the evolution of the system. self-organized criticality, okay, chaos. When a word to chaos, then what is chaos? So as far as I understand, so I'm reading a book now, but is that our systems which are extremely dependent on the initial conditions, yeah? So very, very now narrow discussion. So when the initial conditions, so the butterfly effect is here, you know that. So it's that when something happens in the weather in the north of the Pacific, it can change the weather in the south of the Atlantic. But so the butterfly effect is that by very little changes in the initial conditions gives a totally different behavior of a system, of a weather or something like that. This is phenomenal. So we have to realize that it can happen in society where very, very little things are changing and with dramatic effects. This picture is also very well known, which is called the Edward Lorenz attractor, and it comes out from theory and represents. So this is then discovered with the mathematics around it. This has been discovered and designed, drawn. All that the interaction and the initial conditions play a role. But I leave the further description that is that's so simple. Okay, then nonlinearity. I have already described something. Sophisticated forecasting algorithm. Yeah, probabilistic in nature. Tipping points. We know that from climate change. Phase transition point. Is that do we with our greenhouse gases are we getting to tipping points, and when crossing the tipping point, there is the possibility of getting into irreversible situations. Yeah, so which not reconstructible. Okay, power law is very interesting. Power law is we know that all there is something. I show a picture. I go first to the picture to explain. Here, this picture is where the power law has been extracted. It's the internet representation, the physical structure. So when we look at that and say, yeah, what the communications, the data flows in such a system, well, spontaneously, well, I would say, well, you know, probably what's happening there is similar or can be presented by a bell curve. So the Boltzmann curve, the bell curve, which is statistically well known. So, yeah, okay. And in fact, so that with complexity and especially attracting or investigating the network, it is not so. It is not a bell curve. It is what is then called a power law. And what does that mean? That means that, I give another example, that this here, this should represent or represents de facto the metabolism of a bacteria. Yeah? So there is biochemical pathways, you can check it. Both systems in fact behave as a power law, not as a bell curve. And what means a power law? This is a log-log presentation, but that's not so many. That is that there is a linear correlation, not a bell curve, but a linear correlation with very few elements having a lot of interactions. There's very few with a lot of interactions, and then, so further down, quite a lot with very few interactions. So that means, so that description, so when there is no mathematics around it, this property is vital. And in case of bacteria, for the pharmaceutical industry, what is important that is important to know what are exactly the few elements with a lot of interactions. Then if these are vulnerable to infections or what or other, then the pharmaceutical is say, well, okay, we address these vulnerable elements of that chain, of that system. So this is extremely, it sounds very theoretical, but in fact, the consequences are very, very practical. And now, so as to one word more, then it's so fascinating that I come back to the property where we were. Oh no, sorry, I have to go the other way. Excuse me. Nonlinearity, power laws. Here we are. So networks as for example, the internet. The internet is extremely resilient. So what does it mean? That is that if somewhere on the earth there were, and that happens all the time, a couple hundred multiplexers get on, the internet remains what it is. So unless that one reaches and can kill a very important network, or a variant, so as the Pentagon, or something like that. Yeah. So I don't know. But apart from that, the systems are very, very resilient, which is quite important. Now, good. Let me go further. There's another resilience vulnerability, I've said it. Climate change, the climate change models do apply these type of analysis and identifying dangerous tipping points, irreversible tipping points. Financial markets, so we only can regret that the science is too new. So anyway, so there are a number of complex systems, there are a number of properties there. Now already identified, published, etc. So this is a synthesis, complex adaptive systems, a theory that maintains that the universe is full of systems, whether it's immune systems, social, etc., and that these systems are complex and constantly adapting to their environment. Okay? So strongly to the adaptive and then complex all around us. Most things we take for granted are complex adaptive systems, and the agents in every system exist and behave in total ignorance of the concept, but that does not impede their contribution to the system. So all that, so the independence towards the data. Tools and techniques, let me not too long. So these are what is used in analysis and in constructing models. We have discussed that. So what is used? Data mining may be known. So we have an immense amount of data, but largely not enough for completeness, but nevertheless, so the data mining has a good future in the context of these analysis. Scenario modeling, I spoke about that. Sensitivity analysis of the behavior of complex systems. This is more dynamic system modeling. So these are techniques that come into. And so at the end of let's say the broad introduction, the picture, we tried, you and myself, to give that understandable. And now to end, a few slides about practical examples. So these come out of publications, the two I mentioned, traffic analysis. So there is a term surprise modeling. Yeah. So can we do something there with sophisticated models? Most likely so. Then okay, what we see there is much more behind. Pattern in other complex systems, the European Union is there, use them to presage outbreaks of violence. Okay, U.S. Department of Defense, online prediction of markets, yes, agent-based model, etc. So there is a growing application. I have to skip and come back to that. Here, the food crisis. Why do food crisis? What are the consequences of food crisis? And political instability in North Africa, the Middle East, yeah, and also in Central Africa with Rwanda and others, yeah. So that indeed food hunger, food shortage, etc. Is bringing violence, and coincides with large peaks of global food prices. So the increasing Egypt. Remember that the initial spark was a local guy who couldn't buy or didn't find the bread and committed suicide, and that was igniting an whole movement. So these elements, if one can identify, so the impact on the social impact of food prices, so that would be an application. Good. I go to the next. So now I come back to the order. Here I gave what I know of my own, let's say, library examples. They're all on the internet. Complex adaptive systems and challenging of sustainability is very interesting by Simon Levin. In 2012, this is very recent. Nonlinear detection of paleoclimatic variability transitions, possibly related to human evolution. That is someone from the Potsdam Institute of Climate Research, and published, so PIC is it, and PIC stands for Potsdam Institute for Klimaforschung, and published in the National Academy of Sciences in the US. 2011, Network Driving Forcing Global Environmental Change. That guy is met here in Brussels. He's located in Stockholm in the research institute, the Resilience Center Research Center. Growth, innovation, scaling, and the pace of life in cities. By Betancourt and a couple and other authors, is working at Los Alamos and in the Santa Fe Institute. Is 2007. Complexity and limits to ecological engineering is 2002. Is somewhat older. So these are scientific publications available for consultation, for reading, for inspiration. And so now I come here to the Santa Fe Institute, who has been, so far as I know, at the very beginning of structured complex research, and have a number of fields. Oh, yeah, a number of fields they deal with. It's quite large, and 2 years ago I visited the Santa Fe Institute, and then this is the very end. Yes, it's almost the very end. So I hope that somewhat clarifying explanations, and so with a concern. So for what is it used? Yeah, is this now the mathematical hobbyists who investigate and are pleased to publish that? Now it is going much further, and this year, so beyond concepts, methods, etc. It focuses attention on dynamic connections and evolution, and then some conceptual implications for policymakers. Predictability, identifying and analyzing trends and probabilities. Think of the banking system. think on the depth system. These are applications and probably done, maybe not published, but certainly done now, but too late. And well, as far as I know, outside of the political establishment. But good, anyway, that's not sure. Traditionally, an inability to make a definite prediction has been considered a scientific inadequacy. It will be challenging to move beyond the strict determinism and to effectively engage in decision-making under conditions of uncertainty and complexity. These are very, very strong statements, actually. Yeah. So the strict determinism, so what comes in place, it is in statistics. Brijovin has said that, has described that in superb books. We find it back here. And so that engage in decision-making processes under conditions of uncertainty, not always known, not always visible with the usual techniques of uncertainty and complexity. So, 1, 2, control. As with prediction, control is generally made possible by identifying cause and effect change. In other words, deterministic. And then manipulating the causes. Okay, in the best case. Complexity sciences offers many insights into finding and exploiting desirable attractors, identifying and avoiding dangerous tipping points. That is what we're facing today with climate change. Yeah? This is not out of the blue skies. This is real reality mankind is facing. And recognizing when a system is in a critical self-organizing state. So this is a further conclusion. So this was the last serious slide. This one I have said. Yeah, that's from Box and Draper. Yeah, 87. I like it very much, but it's to be taken with humor. And here are a number of useful references. Some are recent, some are not older than this century, yeah, except a book from Waldrop writing about the Santa Fe Institute, but the others, and Roger Levin as well, so these are books. But anyway, so as introduction, and some of the names have been mentioned. So far, no, that's much too long. We hope, you and myself, Gary too, I imagine, that we try with the group we have to have some comments or report of research going on, or stimulating ideas for research or research proposal. Not that necessarily the World Academy should get into the research business, but it would be, to my view at least, extremely positive if we could be in a stimulating function for doing research in some domains.